Hello, I am Abdelrahman, an autonomous systems student at Hochschule Bonn-Rhein-Sieg in Germany, and a co-author of this paper titled Context-Aware Task Execution Using Apprenticeship Learning. Our objective was to equip a service robot with the ability to learn how to execute a simple task from a human, and then experientially learn variants of this execution that satisfy different contexts of the task. We then validated the benefits of doing so through a user study. The motivation of this work is the concept of contextual adaptivity. Many tasks can be accomplished without regard to context, but non-adaptive actions are inadequate in real-life scenarios. They could be annoying or unnatural to users, or they may cause execution failures. Contextual adaptivity or context awareness refers to recognizing and adapting to contextual differences and avoiding having to relearn behaviors for every situation or executing the same suboptimal actions. Since contextual knowledge is instinctive to humans, a mechanism for learning contextual behavior can utilize their guidance. This is the idea we were exploring in this work. This can be illustrated by object handovers, a simple collaborative task where an object must be handed over to a person. Robots are usually capable of producing a wide range of trajectories, and some could work better in some contexts than others. For example, moving the end effector lower for a seated person or moving slower when dealing with an elderly person. In this case, we could utilize the maneuverability of the robot's arm by enabling it to perceive these differences to adjust and choose the best way to execute a handover. Our objective was a validated approach to making an ability like handovers a context-adaptive skill as opposed to a static action. The apprenticeship learning strategy combines learning from demonstration and reinforcement learning. The robot observes and learns an execution of the task and then learns to modify that model execution to account for differences in context. We first demonstrate a nominal handover trajectory to a robot like the Toyota HSR, which captures its characteristics using a camera. Then we encode this trajectory in dynamic motion primitives, or DMPs, by learning the underlying initial and final position, trajectory shape, and execution speed parameters. We now have a policy that produces the next end effector position at each time step, given the current state, to replicate the demonstrated motion. We call it static in the sense that its parameters are not adjustable at this point. We then define context variables and map them to the adjustable parameters of the DMPs. This allows us to learn different variants of the demonstrated trajectory by adjusting the values of these parameters to execute the motion most optimally for each of these contexts. For example, the receiver could be standing up, seated, or lying down, which would influence the optimal handover position. That would be final trajectory position G, so we'd have to determine G given C1. We can define other contexts like obstacle presence and object fragility and map them to other learnable parameters of the DMPs. Finally, we use a policy search algorithm to learn these mappings by trial and error. We use the contextual relative entropy policy search algorithm, which introduces these mappings as an upper-level policy. The DMP lower-level policy is parameterized by the output omega. Adding the dependence on omega makes this previously static policy contextually adaptive, because it would now produce different behaviors according to the value of C. With the DMP formulation, such a policy can be learned using simulated trajectories, avoiding trials on the real robot, which could be costly. For learning a policy that chooses the optimal G given receiver posture, we crafted a reward function that indicates what is theoretically best in each situation. We define ideal handover positions for each context, G hat, and reward episodes of experience based on how close the sample G is to the G hat of the current context. This constitutes contextual information injected into the learning process. Eventually, the policy output reasonably converges to these positions. The final result is different context-dependent trajectory outputs. Initially, the points sampled by the policy were constrained to a single line, and the values of sigma, governing the rate of exploration, diminished too quickly after a few iterations. We found that performance was best with two modifications, using context vectors and regularly resetting exploration parameters. We motivate these modifications to the algorithm in the following. This diagram shows the algorithm's exploration behavior initially, after applying each of the aforementioned modifications, and after combining the two. We first used vectors for context variables instead of scalars. This increases the number of parameters to be learned but enables exploring along different lines. This causes the algorithm to escape the single line constraint, but it still adheres to sampling points along these lines with no lateral exploration. We then regularly reset the values of sigma by sampling from a uniform distribution in an idea similar to a random restart hill climbing, where local minima are avoided using a similar trick. The result is some lateral exploration, even though the algorithm sticks to sampling points generally around a single line. However, combining the two yielded the best results, where the algorithm explores well and eventually converges to the desired points. We believe a correlated exploration strategy enabled by a sigma matrix with off-diagonal elements contributed to more productive exploration. We transferred the learn policy to the robot and evaluated its effect on users through a simple study. 10 participants received a water bottle from a Toyota HSR in the 3 contexts shown in the image under 2 behavior modes. In the context unaware mode, the robot simply executed the original demonstrated motion. In the context aware mode, it attempted to perceive the person, identify their posture, sample a handover position from the learned policy, and then execute the motion. We randomized the order of contexts and modes between participants to break possible correlations. The objective was to conclude whether they would significantly prefer the context-aware behavior in order to validate the benefits of the learned skill. To perform the task, the HSR detects the person and infers whether the receiver is standing, seated, or lying down. Given this value of C1, the learned policy selects a handover position G and passes it on to the lower-level policy to execute the handover trajectory. For deciding when to release the object, we implemented a force-based detection strategy where we used the robot's wrist sensor to determine when the receiver is trying to pull the object. We used a change detection algorithm to determine when force measurements most likely indicated that the person was pulling with the intent of receiving the object. A software implementation of the skill is available in our GitHub repositories. The questionnaire consisted of 3 parts. After the 3 handovers under each mode, the users had to answer the same 9 questions from strong disagreement to strong agreement. These dealt with criteria like how natural or predictable the robot's behavior felt, how suitable it was for the current situation, and how comfortable or effortless it was to receive the object. Then they had to grade their relative preference over the 2 modes on the same scale. Finally, they had to answer 3 open-ended questions intended to gather additional insights. This chart visualizes the result of the first part of the questionnaire. In particular, it shows how positively the users rated different behavioral aspects of the robot under each mode. The figure illustrates a general inclination towards the second adaptive behavior, which felt more natural and comfortable to users, although some aspects such as perceived safety did not significantly differ between modes. In the second part of the questionnaire, 6 out of the 10 participants indicated they strongly preferred B2, 2 just preferred it, and 2 just preferred B1. In summary, we applied an approach to acquiring a robot skill and making it generalizable to the different contexts of a task using apprenticeship learning. Our variant of CREP successfully learned policies that enabled context-adaptive handover executions from simulations. Regular restarts of exploration parameters and correlated exploration were found to improve learning performance. From the user study, we confirmed our hypothesis that users would instinctively prefer the context-aware behavior enabled by the learned contextual policy. In future work, we could explore learning context-dependent trajectory shape and execution speed parameters and integrating them into the skill. In addition, non-parametric extensions of the CREP's algorithm, which do not rely on a linear Gaussian model, could be used. Gaussian processes can be useful function approximators to use as a policy representation, to model a complex reward function, or as a forward dynamics model. Finally, it would be interesting to approximate the reward from multiple demonstrations using inverse reinforcement learning, instead of having to engineer the reward function ourselves. Thank you.